All right, let's talk about rational functions and their behavior when x goes to infinity or negative infinity. Turns out some of them have horizontal asymptotes and some of them don't. And it all has to do with how fast the top and bottom grow. Now, we've got some rules here that tell us if what happens if the top has greater degree and if the bottom has greater degree. But instead of just memorizing that, let's work this up a little bit. Um, let's look at this. First off, polynomials grow faster if they have higher degree. If I were to graph y equals x squared and y equals x cubed here, y equals x cubed grows faster than y equals x squared. That just makes good sense. If I put in y equals x to the, instead of cubed, if I keep making this larger and larger, it's going to grow faster. If I put in some insane number like 100, it almost looks like a square there because it's growing so fast. Once you get past 1, this is growing insanely fast. So if you have a rational function, let's just put a rational function together. Let's do x squared plus 1 on top and x cubed plus 1 on bottom. All right. If you look at this, think about what happens when x grows large. You start out when when x is 0, you wind up with 1 over 1, which is 1. When x is, say, 5, you get 26 on top and 126 on bottom. Then think about what happens when x gets bigger and bigger. If x is 10, let's come out here and look at the value here. When x is 10, this is y is about 0.1. If you think about what's going on here, when x is 10, the top is 101 and the bottom's 1001. So it's right at a tenth. When x is 100, the top's 10,001 and the bottom's 1,000,001. So as x grows larger and larger, the y value here is going to shrink to 0. And we can see that from our graph here. As x grows larger and larger, this shrinks down to 0. Same thing happens if we go in the opposite direction. So let's change this up a little bit. Suppose I change the bottom to also just be x squared plus 1. Well, we get the same thing everywhere. This is always 1. If I put in some other stuff on the bottom, say x squared plus x plus 1, then what happens is when x grows large, this approaches 1. If I zoom way out, it's kind of hard to see, but if I zoom way out, it approaches 1 on both sides. So let's go back for a second. If this is x cubed plus 1 or plus 3, whatever, if we have a higher degree on bottom, then we're going to wind up getting a horizontal asymptote at x equals 0. And notice that's regardless of what the rest of the stuff is. If I change this up here to, say, 10x squared plus 5x plus 10. It changes the behavior of the graph and stuff. But eventually what happens is, when you're computing this, the dominant term is going to be the thing that determines the overall size of the numerator and denominator. Dominant term down here is x cubed, dominant one up here is 10x squared. And if you look at what happens here, when x grows large, y grows to 0. So that gives us the first rule we have here. If the top has I guess that gives us the second rule here. If the bottom has greater degree, then we get 0 for a horizontal asymptote. If the top has greater degree, then the limits are either going to be positive or negative infinity. Let's play with some examples of that. So up here, if I give the top greater degree, say 10x, the bottom has degree 3. If I give this a degree of 4, it's not a very interesting graph, but as x grows large, this goes to infinity. And as x grows large in the negative, y goes to negative infinity. That's not a very easy one to see. Let me put another one in. Let's say I've got x squared plus 3 over 2x minus 4. So yeah, as x grows large, this goes to infinity. As x grows large negative, this goes to negative infinity. Now, what about if we have the same degree on top and bottom? If I change that to 2x to the 4th, or 2x squared minus 4 under x squared plus 3, if you notice, we do have an asymptote here. It's not easy to see here, but this asymptote is a half. Let me adjust this slightly. I'm going to make my y-axis, I'm going to zoom way in on it. Let me pull this in so we can see what we're doing. On the y-axis, let's just go from, say, negative 3 to 3. All right. So this graph now, it's got a few different parts to it. But notice, let's see, this is 2. If I zoom in a little more, we can see. Yeah, as x grows large, this is approaching 1/2. Same thing in the other direction. If I change this up here to 4x squared, now that changed our asymptote to 2. The reason is, as x grows large, the only thing that matters on the function is the leading terms. And up top we've got 4x squared, and on bottom we got 2x squared. Well, what happens when x grows large, the 3 and the 4 don't matter. And the x squareds are the same on top and bottom. It's just one of them is multiplied by 4, the other is multiplied by 2. So what we wind up with here is that the asymptotes are going to be the leading, the ratio of the leading coefficients. In this case, the asymptote is 4 over 2, which is 2. If I wanted to put the asymptote, say, at 3, I just need to change this up here to 6, and that bumps it up there. If I change this to, say, 7, 6 over 7, my asymptote's here at 6 over 7. All right, so let's do some examples. Okay, for these examples, again, all we have to look at on these is the leading term on top and bottom. So up top we've got 2x squared, and on bottom we've got negative 5x. Now, the top has higher degree than the bottom, therefore this is going to be positive or negative infinity. The way we figure this out is, up top, we've got 2 times infinity squared. And on the bottom, we've got negative 5 times infinity. All right, so this is going to be negative infinity. Excuse me. You can think of this informally as being, this cancels with one of those infinities. The 2/5, you wind up with essentially negative 2/5 times infinity, which gives you negative infinity. Let's look at the next one. All right, we got 9x squared over negative 4x cubed. Okay, we don't need to do anything more with this. We've got a higher degree on the bottom. I just realized I've got a typo here. Or actually, it's not, well, it is a typo, but let's look at it. I've got 2x cubed terms here. I should really combine those before I do any limits. You shouldn't run into that. But if it happens, you got to put them together. So this is negative 4 No, negative 4 plus 1 is negative 3. But still, actually, the only thing that's important here is the bottom has higher degree. So this limit is going to be 0. Bottom having higher degree gives you a limit of 0. It doesn't matter if it's positive or negative infinity. Either one is going to give you 0 there. Okay, this next one, we've got x cubed on top and 5x cubed on bottom. So again, this one, all we have to do, since they're the same degree, is get the ratio of the leading coefficients. And this one down here is the same thing. X is going to negative infinity, but we've got 3x over 5x, so this is going to be 3/5. All right. Let's do one more example. I'm going to make an example E here. Limit as x goes to negative infinity of minus x to the 4th plus 3x squared over 2x plus 5. All right. Now, the top has higher degree than the bottom, so that tells us it's going to be either positive or negative infinity. Now we just have to figure out the signs here. Up top, what we have is, I'll write this beneath, we've got negative, and then we've got negative infinity to the 4th. On the bottom, we've got 2 times negative infinity. So this is going to be infinity, but to decide if it's positive or negative, we have to count the number of negatives that we have here. We've got a total of 1, 2, 3, 4, 5, 6 negatives. So even number of negatives makes a positive. So the answer to this one is positive infinity. Oh, I didn't realize I have another example here. Whatever. We'll call that example F up there. Example E. X is going to negative infinity. Now on top we've got a higher degree. So we know it's going to be positive or negative infinity. So this is going to be, up top we've got 3 times negative infinity squared. And on bottom we've got 5 times negative infinity. So we know this is going to be infinity or negative infinity. How many negatives do we have total? Let's see, 1, 2, 3. So 3 negatives, so this one is going to be negative infinity. And you can always go and check your answers on these things by using Desmos. Now, if I gave you this problem on a test or on a graded homework, I'd want you to show me what you're doing, but definitely check it on Desmos. If I come over here to Desmos and I put this in, y equals 3x squared plus 4 over 5x minus 7. Let's see, I've got an extra y equals, let me take that out. And it's asking us, what does this do when x goes to negative infinity? Well, let's zoom way the heck out. When x goes to negative infinity, this is going down. So that sure enough tells us the answer is negative infinity. It's good to check your answers like that. All right, now what I've been showing you, I kind of skipped over the fact that that's the informal method of doing that. There's a formal method for doing this too, and we'll look at the formal method in the next video.